in this MTT student branch chapter of IIIT DM Jabalpur, and just I just put my topic as basically this planar antennas as a recent research trend. So basically, what does mean? What is going on these recent trends? I would like to let you know. Okay, so my introduction part is over. So I don't want to talk too much about my institutions because everybody is knowing what is IIT BHU, and maybe you can explore what kind of facilities are available in my laboratories. So you can go my web page on Department of Electronics Engineering. There you'll find the profile. So you can go my profile and just student can search, and also faculty can also search in further collaborations, future collaborations. So definitely we can do something in a good manner in the futures. And I have already collaborated with Dr. Manoj and the Dr. Dinesh regarding same, and we have submitted one project recently to the ISRO. So obviously we are hoping so we will get the collaborative projects. So we will doing something good one. So in conclusion of this one, so I think most of the students, so they are from the micro engineering side.
Yes, sir. Yes, sir.
Okay. Okay. So it's good. So basically, you are very much aware of this background of the planar antennas. I hope. So you know that in 1952, my slide is visible?
Yes, sir.
Yes, sir.
Okay, let me put in the, okay, now it is okay. So this basically two gentlemen, you can find Greg and Engelman, two gentlemen, they were given in concept of microstrip technology in 1952. Okay, so you can see this is the idea, and they given an idea of microstrip as a new transmission line. Okay, so in the 1952, just idea of transmission line came into pictures, which was given by two gentlemen. And that time the range written in basically kilo megacycles. If you'll see kilo megacycle, so just students, can you just recall this kilo megacycle? Right now we are saying hertz, gigahertz, megahertz, all those things. So what do you mean by the kilo megacycle? Student, please. What does it mean by the kilo megacycle?
I think it should be giga. I mean, kilo times of mega means.
So you are not confident about this one?
Sir, kilo mega, I think it should be. I mean, I haven't read it anywhere, but I think it should be
kilo
giga.
Is there and mega is there.
Sir, it should be
Kilo
giga.
Is there, mega is there.
It becomes giga.
So it becomes a giga, right? And cycle is hertz. Okay, so this is the gigahertz. Okay, but that time it is written in like that. Okay, kilo megacycles, megacycle like that. Okay, so this is a new transmission line which was introduced by this Greg and Engelman. Okay, so it is clear. Then you can see within a year. Okay, this has given an idea of microstrip antenna. Okay, microstrip as a microwave antennas. Okay, so this is the first time the idea of microstrip planar antenna comes into pictures in 1953. This was given by the Deschamps. Okay, so it is already noted in the book. So you will find any book. So you will find the Deschamps idea is comes into 1953 as a micro antennas. Okay, exactly after the 2 decades in 72 and 74, you can see the 72, 52 to 72, exactly two decades. A practical antennas has been proposed. Okay, so practical method comes to pictures that was given by the Howell and Munson. The Howell gives the microstrip antennas ideas, and Munson gives the microstrip as an array. Okay, microstrip antenna as an array. Okay, these are the idea came into picture in 1972 and 74. So these are the basic things. Everybody should know these things. This is the historical background, how microstrip antenna came into the picture. We can say how the planar antenna came into the picture. Okay, so now you just heard the word microstrip and microstrip antenna, microstrip line. Okay, so my question to the students is that what is microstrip? What do you mean by the microstrip?
Sir, as we have understood, it is a strip line having a wavelength in the range of micrometers. Means,
Micrometer.
yes, sir. In the frequency of gigahertz, if we operate, then the size
Okay.
of the strip lines is in the micrometer range, 150 micrometer, 100 micrometer, 500 micrometer. So,
Okay. 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 My next questions, basically, before that, you should know what is microwave. So can anybody tell something on what is microwave? We can say why microwave is called microwave. Why microwave is called microwave? Are you getting my question? Are you getting
hello,
my question? Yeah.
yes,
Why microwave is called microwave?
sir.
Yeah.
I think it's the frequency which converts things into wavelength, which
Yeah.
is the micrometer range.
Micrometer range means your answer is remain same. Micrometer range. Micrometer means
10 is power minus 6
10
meter,
per minus
minus 6 meter.
minus 6 meter.
Yes, sir.
Okay. Chalo. So micro means 10 per minus 6 meter or something else?
Basically, if in a layman language, micro means small, very small.
Very small. It's in comparison to other waves.
Okay, I'm just talking about first micrometer. Whatever you talking about the micrometer. Okay.
In micrometer, micro means 10 is power minus 6.
10 per minus 6. Okay. 10 per minus 6 meter. Okay. So you can convert it to millimeter also.
Yes, sir. It is 10 is power minus 3 meter.
10 per minus 3.
1000 millimeter.
Yes, sir. Milli means 10 is power minus 3.
And 1000 millimeter.
Yes, sir. If we're talking about a micrometer, then it will be 1000 millimeter.
1000 millimeter.
Yeah.
1000 10 is power minus 3 means 10 is power minus 3 millimeter. It should be. If we talk
Okay.
about 1 micrometer to millimeter conversion, then it should be 10 is power minus 3 millimeter. Yes.
Okay. And what is the frequency range used in the microwave? Yeah, designated for the microwave.
For microwave, we take
1 megahertz to
gigahertz. The frequency
1
should
megahertz to 1 megahertz to
no, sir. It is 0.3 gigahertz to
0.3 gigahertz. We can say okay, 300 megahertz. Okay.
yes, sir. From 300 megahertz to 3 gigahertz, I think.
3 gigahertz. Yeah. Someone can rectify it.
300 megahertz to 30 gigahertz, it's microwave, and then millimeter wave 30 gigahertz to 300 gigahertz.
Okay. And above. Okay. Now you can see in the within the range of 300 megahertz to 30 gigahertz. What would be the wavelength? Corresponding to 30 megahertz, what would the wavelength? And 3 gigahertz, what would the wavelength? Yeah. There is no need of any calculation or calculators. You can just directly calculate. In 30 gigahertz, the wavelength would be 10.
Yes, sir. 10 millimeter.
10 millimeters. Similarly, over here, it would be 100.
Yes, sir.
Okay. So you can convert into the 10 centimeter. It would be 1 centimeter.
Yes, sir.
yes.
So where is the micrometer then?
Yes, sir. That's what I read in the books. Yeah. That it should be. It is very small. Means
Yeah.
1
So
millimeter.
if you are
not a
telling like
micrometer.
so we didn't find any wavelength within the range of micrometers.
Yes, sir.
Okay.
Absolutely.
So we can't say the microwave is called based on this wavelength phenomena. Okay.
Yes, sir.
We can't say this is a wavelength in the micrometers.
Yes, yes.
So obviously, based on the results, you can see that time. So it is a very tiny wavelength.
Yes, sir.
This is a very tiny thing. Okay, the tiny wavelength. Because of tiny things, so that time and that particular era, what is happening? Any thing or any object which cannot be seized by the naked eye, cannot seen by the naked eye. Okay, means very, very tiny, like you can see microscope.
Yes, sir. In the time of 1953. So
Yeah, exactly. So that time, any tiny objects or tiny things, they are just using the word micro. Okay.
yes,
No,
sir.
that time no one think about this centimeter wave or millimeter wave or something else like that. So immediately, okay, some wavelength is okay, some wave is there, and it's very tiny. We can say with the naked eye. So they're given the name is because of these tiny words, a tiny wavelength. Never think about this wavelength in the millimeters or centimeters or micrometers. Okay, no one think about that, and given this because of these tiny words, given the name microwave only. Okay, so there is no correlation and no relation with the 10 to the power minus micrometers. Okay, is clear?
Yes, sir.
Similar. So there is no relation of microstrip with the micrometer
Micrometers.
wavelength. Okay,
Yes, sir.
it is clear.
Yes, sir. It's clear.
So
Thank you.
sometimes micro. Okay, let me show. Okay, we will discuss in next slide. So what would be better? Okay. So I don't think we have to discuss the advantages of the microstrip antennas. So everybody is knowing, right? So I can skip this one.
Yes, sir.
So everyone is knowing because of this planar technologies, we can say the printed circuit board technology. It has a lightweight, low volume, and thin profile configurations. Okay. So because of that, it can be made conformal. Okay. So it can take any shape. Okay. And because of the printed circuit board technology, it has a low fabrication cost, so that we can produce in a mass, right? And polarization wise, it is possible by making small and simple and minute changes in the feed systems, feed networks, and you can basically create linear and circular polarizations. It is possible with the help of reconfigurability. Nowadays, it is possible. We can achieve polarization reconfigurability where we can have the linear to circular, circular to radial also. Okay. So these are some advantages. So I'm not discussing about too much in details. But before that, I hope you guys have already read this 2 books and 1 article. Okay. So this article is very important one, published in 81 by the given published by Carver and Mink. This is the microstrip antenna technology. Okay. So before that, you can see there are 2 books I have listed over here. The book's name is the Bahal Bhartiya Antenna Microstrip Antenna, published by Artec House. Okay, these books come into basically the 1980s, and they have incorporated entire paper published between the duration of 70s to 80s. Okay, they have incorporated all those things, and there they basically discuss about the what is microstrip antennas, what types of microstrips, there are different configurations, their analysis techniques. Various analysis, the various kind of shape they have discussed in Bahal and Bharti, and they discuss about their analysis technique also. Even they discuss various analytical models. Okay, based on that, you can analyze the simple configuration of any microstrip antenna. Okay, so nowadays we guys are not using the analytical technique. You are using the numerical technique because our geometry becomes complex. Okay, so once geometry becomes complex, when that we can say, or the partial differential equation which is associated with the problem, it becomes complex. So it would be very difficult to resolve the issue with the help of analytical technique. Just remove the numerical techniques. Okay, and there are a variety of numerical techniques are available. You guys are known very well. Okay, now second books also you can see James Hall and Wood. Okay, it is published in a similar year, so same 81. Okay. So the details you will find the analysis and design aspects of the microstrip antennas. Same, you can just find all entire things, whatever written in the Bahal and Bhartiya, you will find in the details. Okay, but the Carver and Mink, this given the article, this is microstrip antenna technology. So this is a 23-page paper where you will find the entire analysis of a patch antenna, which is given in Bahal, Bhartiya as well as James and Hall book. Okay, so if you didn't find a time to read these 2 books, and if you'll just find a time to download this from the IEEE sites and once go through this 23 pages paper, so you can understand basically what is microstrip antennas, how you can analyze by analytical methods, and so on. So now just wait. Okay, I just forget to put. Okay, so now what I'm discussing basically before, what is microstrip antennas? Okay, so basically we can't say the strip. Basically microstrip, basically there are a variety of lines. Microstrip line is different, strip line is different, slot line is different. Okay, and their configurations are different. Okay, so microstrip means when the dielectric sandwich between two conducting layers. Okay, any dielectric which is sandwiched between two conducting layers, that structure is called, that configuration called microstrip. Okay, so means I mean to say, suppose this is the cross section I am putting over here. This is the cross sections, any dielectric materials, which this is dielectric materials. Okay, this is conducting materials, and this is also one conducting materials. So this is the ground, and this is any structures. Okay, metallic structure. Okay, so this is a conductor. This is also a conductor, and this is dielectric. So when dielectric, which is sandwiched between two conducting layers, you will find such kind of structures anywhere. Configuration you think about, this is a microstrip. Okay, so this word coming to pictures based on that microstrip. Okay, so right now there is no relationship with the micro. Okay, that means micrometers. Okay, because it is invented in, you have seen, in the 1952. Okay, in the same era, same time, 1952, there is no relation with the 10⁻⁻⁶ meters. Okay, wavelength. Okay, now you can see there is a line and antenna. There are two different terminologies have been invented. Microstrip line as in microstrip antenna. So once you see microstrip line, that means the width. Line means it can be of any length. Line means it can be of any length, transmission line having any infinite length. Okay, we cannot restrict for length, but width is very important.
Doctor, we can't see what you're doing.
Pardon?
We cannot see what you are drawing. It is not on the screen.
Oh, it is not on the, okay.
Sir, in my screen, it is visible. I would like to ask other participants also whether they can see
Yes, it is visible.
or not.
Oh, it is visible?
Yes, it is visible.
Okay.
So Daniel sir, I think there is some issue with the screen you are using.
Okay.
Because other participants are able to see the drawings sir is making.
Okay. So there are two things. So what I told you, just line and the antennas. Okay. So in antenna case, so I think microstrip is very much clear. So I
Yes,
put
sir.
microstrip as a, when dielectric, which is sandwiched between two conducting layers, that can be considered the microstrip. There is no relationship with the wavelength in the micrometers. Okay. Because the same times is considered in the 1953. Now, microstrip line and microstrip antenna. So in the line may be of any length, it can be of infinite length, but antenna, there is a restrictions related to width and length. Okay, so it should be radiating. The structure should be radiating. Once structure is radiating, that means we can say this is the antenna. But in the case of line, we have to transmit the signal from one end to another end. That means your line cannot radiate. In that case, your width is very, very smaller than the length. Okay, and the antenna case, the width is almost approximately, yeah, we can say close to the length, yeah, comparable to the length. Okay, but here we can see width is very, very less than length. Okay, so based on that we can define microstrip line as well as the microstrip antenna. I think it is very much clear.
Yes, sir.
Okay. Now these are some potential areas of microstrip planar antennas. So nowadays everyone is using the RFIDs in your iCards, in everywhere, in your any shop when you are visiting, any malls and visiting. So there are RFID readers, and the RFID tags attached to the articles. Okay, and small ultra wideband antennas nowadays using for many applications, including cognitive radios. Okay, so in the cognitive radio, there are two types of antennas are using, one for sensing the spectrum signals and another for transmitting the signal. Okay, and the arrays, in the case of array, this is a special kind of arrays we can make for desired gain in patterns. Okay, and also you can see in the ultra wideband antenna, I written the good performance. The word which I put specifically, we can't say more. Nowadays research is going on just designing an UWB antenna. But what does it mean, the good performance? UWB antenna with good performance. So what does mean good performance? Means what do you understand by the
Radiation
good word?
efficiency.
Pardon?
It's sorry, radiation efficiency.
You are
there
talking about
are
efficiency.
So there
Yes,
are some
radiation efficiency.
parameters on which an antenna
And,
performance is dependent, such as antenna gain, antenna efficiency, directivity. So I think these are the parameters which they have considered, and they are
Okay.
giving good output, so they have taken it as good performance.
Okay, before that, I have a very small question. Maybe antenna guy can answer. How can you define the ultra wideband?
it have 20% bandwidth of the center frequency, more than 20%.
Okay.
Yes.
Okay. Anything else?
The range of frequency is from 3.1 gigahertz to 10.6 gigahertz, sir.
Okay.
Ultra wideband, which is decided by FCC.
Okay.
Yes.
Yeah. This is the frequency range given by the FCC for the application of
Yes.
this
Ultra
UWB.
wideband.
Say this is a UWB.
Yes.
Okay. A frequency band, absolute frequency base greater than or equal to 500 megahertz. Okay, can be considered as a UWB. Another definition, this is the fractional bandwidth. This is fractional bandwidth which should be greater than or equal to 20%.
20%.
Fractional bandwidth is 20%, right?
Yes, sir. Yes, sir.
So based on this fractional bandwidths, okay, maybe this is good for the students. Okay. So this fractional bandwidths, how can you define this fractional bandwidth? Yeah, okay. I am just asking this question in different way. Okay. What would be the maximum fractional bandwidth of any antennas? I think question is very much clear.
Yes, sir.
What would be the maximum fractional, theoretically, what would be the maximum fractional bandwidth of any antenna? If you know the formula of fractional bandwidth, so you can very easily, yeah.
In practically, we can get around 80% also.
80%.
Yes.
What is the formula of fractional bandwidth?
It's cutoff frequency between 10 dB with the 10 dB return loss, lower to higher cutoff frequency, difference between lower to higher cutoff frequency upon the center frequency of the antenna.
You are talking about that one, right?
Yes, yes, yes.
Okay. So what does it mean?
Higher cutoff frequency.
Based on that, you can see what would be the maximum.
Higher cutoff frequency. It has the.
So we can say, we can write like that. Suppose FH minus FL, FH plus FL. 2. Okay, this is multiplied by 2. By 2, I just put what?
Yes.
Okay. So what would the maximum one into 100? Okay.
Yes, sir.
What would the maximum?
200%, sir. When we are putting FL is equals to 0.
200%, because this is too high. Okay. So theoretically, the fractional bandwidth of any antenna can be 200%. Okay, so that's why you can see nowadays any paper you need refer for UWB antenna, you can find fractional bandwidth of 167%, 178% like that.
Yes, sir.
So maybe sometimes you never think about that, why this frequency band is coming. You are just focusing only this particular 3.1 to 10.6 gigahertz band and their center frequency, right?
Yes.
Okay, just think about that, how this figure is coming. So theoretically, it is possible we can achieve up to the 200 megahertz or 200%. Okay, right? It's theoretically possible. Okay,
yes.
So these are potential areas. So good performance means, so UWB, this is FCC given the frequency band where we can use 3.1 to 10.6 gigahertz band. Okay, this is unlicensed band. Okay, so what is happening within this band? There is certain spectrum of the signal, transmitted signal. Okay, is clear?
Yes, sir.
That is called EIRP.
Yes.
Okay. So Manoj?
Yes, sir. Yes, sir.
Yeah. I put EIRP is okay, na? Yeah. So you can see, so there is a certain envelope, within this band 3.1 gigahertz to 10.6 gigahertz band. Okay, there is certain envelope. Okay, so within this envelope, okay, there is certain limit had been defined. Okay, how much should be the threshold level? Okay, if we are transmitting a signal within this level, that would be better. Okay, so we have to achieve entire thing within this level. That then you can say your antenna gives a good performance. So I put the words EIRP. What does mean EIRP means?
Equivalent isotropic radiated power.
Immediate, rest of thing is okay. Immediate isotopic radiated power.
Yes, sir. We can say
Not equivalent.
effective. It will be
Not
effective.
effective. Immediate.
Okay. Immediate. Okay, sir.
Immediate.
Okay, sir. Okay, sir. Okay, sir.
Yes. There are just small words. Okay. Just remember. Okay. So FCC is full form is knowing. Federal Communication
Federal
Committee.
Communication Committee.
Exactly. So these small words always remember. Okay. Because these are the very catching words. Always interview words. Take these words and they would like to check. This is for students only. Okay. So they would like to check whether you are knowing these basic things or not. Okay. So this is fine. So you just see good performance. Gain would be one thing and efficiency would be one of the things. But in addition to that, what kind of application you are looking for? Okay. Suppose you are looking for the imaging applications, medical imaging applications. Okay. So in medical imaging applications, what kind of requirement is required? Okay. So accordingly, you have to design your antenna that can satisfy the requirement of that particular application. Then you can say it is good one. Okay. Otherwise, simple designing antenna, you are getting 10 dB return loss bandwidth is okay. You are getting omnidirectional radiation pattern is okay, and you are saying my antenna is good. So this is not sufficient. You have to see what is the immediate EIRP. Okay, you have to check. We are transmitting the signal within this range or not. It is satisfying or not. Further, in addition to that, once you are calculating the gain, okay, so only calculating the gain of the antenna or measuring the gain of the antenna is not a sufficient thing. Okay, for particular applications, when you are suppose node 1, right now everybody is working on the sensor network areas. So node 1 is there, and another node somewhere, some other places, and would like to transmit the signal from node 1 to node 2. Okay, and antenna 1 gain is given G1. Okay, and this antenna node 2 gain is G2, suppose. Once we have these conditions, so whatever G1 we have, this has to be communicated properly with G2. So how it can be possible? It has to, then you have to think about the link design. So another duty of the antenna engineer is to establish a link design, a budget link. Okay, so that you can see, because this node 2, either we have to design this antenna or this antenna properly. Once suppose our node 2 antenna is fixed. Node 2 antenna is fixed. We cannot do this anything with this one. This is fixed, suppose. Then we have to establish a network from node 1 to node 2, and node 2 is fixed. So we have to design an antenna node 1 in such a way that the gain of the antenna 1 meets the criteria this antenna 2. So antenna node 2 gain is knowing. Okay. Transmitted power is knowing. It is knowing. The receiver power is knowing. Okay. So to meet this receive power, how much power is transmitted, that can be calculated based on this gain. So suppose transmitted power is fixed because this envelope, this transmitted power is fixed, we cannot go beyond that. Then we have to play with the antenna gain. So we have to design antenna such a way that we can meet out this particular gain antenna based on the Friis formula. Okay. So you just go through the Friis formula, design the budget link, considering the entire losses between the link. Okay, entire losses includes, one is the free space path loss. Okay, free space path loss is one thing. Rest of the thing, which environment you are living, basically this is the urban environment, rural environments, your room environments, or what kind of scattering environment we have. Okay, so based on that, that environment you have to consider. Always what we are doing, we are considering antenna performance in the free space environment, either in the simulations or in the measurement. We are performing the measurement in the anechoic chamber. When you are performing the measurement in anechoic chambers, we are just creating artificially the free space environment. Okay, and the simulations, this will ideally considers there is no losses. So we are considering the free space environment in both cases. But practically, this is not the scene. Practically, we have the scattering environment, right? So that we consider the multipath environment. We have the reflections, we have the refractions, we have the scattering. There are many things we have in the environments, right? It's clear?
Yes,
so
sir.
some areas also body area network is there, Reconfigure antenna is there. Okay, the printed antenna for unconventional and some even using basically the defective ground structures. And we can say metamaterials. Implantable antennas are there, automatic radars are there. Nowadays in the 5G, basically 5G, I'm talking about the millimeter wave, means 60 to 70 gigahertz. In the 60 to 70 gigahertz, so basically the automotive radars will come into pictures. So basically the antenna, right now the basically Porsche, Mercedes, they are working on these antennas for their own cars. Okay, automatic radars for different collision radars. There are many radars they are putting on their cars, and that would be wireless communications. Okay, that would be wireless. Okay, they never use the wire. Okay, so this is automatic radar they will use in this particular frequency range. So Mercedes Benz and Porsche. So Porsche is the costlier than the Mercedes, so it is one of the sports cars also. The Porsche, that after Mercedes, both are working on this one. So anyone who is working on these high frequencies areas, means millimeter wave areas. So Porsche and Mercedes Benz are looking for those guys, and they are giving a good package. Okay, if any PhD students are interested to work with the Porsche and the Mercedes, so they can go to the Germany. They can go to Germany and join any high frequency laboratory. Okay, under the fellowship of, you can say, if you are master students or PhD students, they can go through the DAD fellowship. Okay, so it's announced by the government of India. So there is a scientific collaboration between the government of India and the German governments. So this is the German Research Foundation. This is the DFG. So you can just go to the site of German Research Foundation DFG, and you can find there are various research opportunities. So if you are antenna guys and would like to join high frequencies laboratories, so Germany is a good destination for them. Okay, just visit Germany, different laboratories, join them, and they will find a good opportunity in the Porsche and the Mercedes to work with them for the high frequency antenna. Okay, so now, now I'm just putting some few pictures and few antennas were there. So might be you have seen somewhere else, or I don't know, have you seen or not? Okay, but this is a special kind of antennas. Okay, so this is the recent trend, what is going on in addition to the research. Okay, whatever I put over there, in addition to these topics, this is the actual practical antennas already installed in the worldwide. Okay, so maybe you guys have seen this kind of vehicle near the borders areas like Ladakh area, Jammu Kashmir area. Have you seen? There is a one big car, and there is a one big briefcase kind of thing, like black briefcase or suitcase kind of thing. Have you seen somewhere sometimes in the border areas?
No, sir. I have never been that fortunate.
Yeah, you maybe some of yeah, maybe in the movies also. Have you seen the movies? Okay, so these are basically the direction finding antennas.
Yes, sir.
Direction finding antennas. Okay, so obviously direction finding antennas. So you can see these pictures. Okay, in left hand side pictures, these are the planar antennas in form in different shapes, along with the biconical horns. Okay, means they are a combination of antennas. Okay, one for detecting the environments, another for a transmitting purpose. Okay, so this is the broadband operation of 20 megahertz to 8.5 gigahertz. Okay, So this 20 megahertz to frequency range is 8.5 gigahertz, or you can think at that basically with 20 megahertz, what is the wavelength? Based on that, you can see the size, and it is accommodated. Everybody is knowing the width of the car, not more than the 4.5 feet. Okay, maximum is 4.5 feet, or 4 feet, right? Right. So within that, you can see within the carrier we have to antenna has to be mounted. Okay, so it is very small one. So this is packed within this one. Okay, so this is radiating in particular directions. So high beam is radiated in particular directions. So like in our areas, Jammu, Ladakh, this such kind of vehicle has been installed. So in collaboration in Army, we have installed one of the antenna in such kind of things. Okay, or there. Okay, so this is professional. This antenna, this guy was made by some German company. Okay, so you can say German or Switzerland company right now. Designed in the Germany and made in collaboration by the Rohde & Schwarz. Okay. So Rohde & Schwarz antennas are designed specifically this one, and this can be mounted on any vehicles, mounted on the tripods. Okay, and using for the direction finding. And accuracy, you can see the accuracy is 2 degree. Okay, RMS, and 1 degree when you are considering in the reflection-free environments. Okay, so 1 degree in reflection-free environment, lab environment. Otherwise, in scattering environment is 2 degree. So 2 degree, this is a high accuracy. Okay, so we can detect the signals which is coming from the enemy sites. This is the purpose. Okay, so what are you getting
what
from?
What is the meaning of 2 degree RMS?
What is RMS? Root mean square. Okay. Divided by square root 2. Well, what is the value? Is the square root 2. Okay, root mean square. Okay.
Yes,
so yeah. So what does it mean the direction finding? What are you getting from this word direction finding? I told you this antenna these guys are using and deployed at the border areas. Okay, in the border areas. So what does it mean direction finding antenna means? What is the purpose? What purpose you are getting?
That basically direction finding may be related with compass, just to point north or getting whether which direction is north or not. But
No,
here I'm not sure
no,
about it.
no. Okay, basically what is happening in border areas? Okay, like us, we are deploying our antennas. Okay, are transmitting as well as detecting the signal from enemy side. Okay, okay. Similarly, they are putting their antennas. Okay, so there are high power transmitters for there. So we have to detect. We are hunting the micro high power sources.
Oh, okay. Yes, sir.
Where the signal is coming from. Okay, so our target, once we are detecting the source where we are getting the signal, okay, from, you just forget about our areas. Okay, we are not looking for our areas. Okay, Indian border we are not looking, just opposite to the Indian borders. Okay, other countries, enemies countries we are looking for, neighboring countries we are looking. Okay, so if any signal is coming from this particular directions, we can see the intensity and we can calculate, we can just locate its location. Our purpose is that, or Indian basically army purpose, defense purpose is that we have to destroy this source. Basically, once they are destroying, basically they are just trespassing or reason basically with the help of this transmitter. Okay, they are sending the signals and they are getting the messages and other things that they are imaging whatever source they have. Okay, so our purpose is to destroy this source. Okay, by maybe putting bullets or bomb or whatever source we have. So we have to destroy these sources. Similarly, our sources they are destroying. Okay, in the border areas, what is happening? Just putting somewhere we are just moving. These are the moving vehicles, so it is not detectable easily. Okay, this is also, you can see this is the portable, not detected very easily. But in fixed areas where we have to put permanently for the transmitting and receiving purpose, and the border area. Suppose we have the mountains in the Ladakh. Okay, so hill of the Ladakh, top of the Ladakh hills, the Indian Army they mount this antenna. Okay, but what is happening? This is the entirely reflected signal. Okay, entirely metallic signal. So just see the practical challenges. Once human being will go there, directly, and they are transmitting the signals. So based on these human bodies, their signal will be absorbed. Okay, immediately they will get the reflected signal back, which is with signal strength will be low. Okay, so immediately they will get someone is there, means someone is that can absorb the signal, that is absorbing the signal. So immediately they can shoot. Okay, so soldier can die immediately. So what Indian Army is doing, means other armies also doing in the same way. So I'm talking about Indian Army because we have like such experience. So they are putting with the help of pole. Okay, use the help of pole and just hide themselves behind the hill. Okay, and putting the rods and mounted antenna over there and just fix and deploy it over there. Okay, and that's getting. So many times this is basically they are hitting and they are destroying many times. So they need lot of antennas over there. This is the immediate requirement of Indian Army, that in the border area they need thousands of antenna, because every day the antenna is destroying. Both sides is happening. Okay, without human loss, but the first thing is that to destroy the communication systems. Okay, so everyone is destroying this communication system. So we are putting to detect their transmitters. Where are their transmitters? Okay, high power transmitters, where they are. Then once we get the signal on the bottom side, immediately we locate and destroy them. Okay. In the similarly, we have seen this is another thing. The antennas are very small. Okay, these antennas are especially designed for naval purposes. Okay, so you can see this antenna in the planar configuration, same, only just the same antenna. You can see this antenna is same. Cars here in the ship, it is mounted, and you can see the radome covered with the radome also. Okay, the entire things, entire electronic circuitry would be there within this port. Okay, entire circuit would be there, so that entire element can read it in different directions. Okay, this is another kind of antenna, and the beauty of this antenna is that you can see this is the world smallest antenna with this range, 10 megahertz to
8 gigahertz.
8.5 gigahertz range. This is the world smallest antenna. Okay, this you can see the size, which is mounted on the car. Okay, and this is the structure. Okay, these are few things. So there are many things which we have to discuss. So these are the practical things I have discussed. So, and there is a time restrictions. So I don't want to move in the next part of the reconfigurable antennas. If you wish, so I can show some examples of the reconfigurable antennas. What do you mean?
Yes, sir, you can see. You can show
Some examples. Okay, I think everybody is knowing what is reconfigurable antennas.
Yes, sir.
Okay, then I'm just. Can you define the reconfigurability in the antenna?
It's varying the bandwidth, or it can vary the band, means resonance frequency from one frequency to other frequency.
Yeah.
Yes.
That is
By
frequency
switching-
reconfigurability you are talking about.
Means the resonance frequency of the antenna or bandwidth of the antenna, we can vary by the switching by the active element.
Okay.
Yes.
Now see the definitions. Reconfigure means simple thing. You can just consider an example of laptop. Okay. Just consider an example of laptop. I'm choosing this example always. Laptop. We have the laptop. Okay. Initially, we bought, suppose we have the laptop, and inbuilt RAM we have suppose 16 GB. Right? We have some SATA hard disk. Okay. Initially. Now, when I bought from the vendors and just find, okay, this RAM is not sufficient for my applications, I need about 64 GB RAM. Sign up slot is available, as also my laptop is compatible with 64 GB. So I asked vendors, okay, just increase my RAM with the 64 GB, right? It is possible?
Yes, sir.
Yes.
Okay. So what we are doing, initially we have some configurations. We are reconfiguring our laptop in such a way that we are just enhancing our RAM from 16 GB to 64 GB, right? In addition to that, we can ask the guy, okay, change my hard disk SATA to some other hard disk. Okay.
Yes, sir.
It is possible. So slot is available, the compatibility is there, so he can remove and he can fix some other hard disk, right?
Yes, sir.
So can we change any config, any the shape and size or form factor, anything? We never change anything, right? We just enhancing the performance of system by replacing some components, right?
Yes, sir.
Whenever we don't need that components, means we don't need the RAM of 64 GB, we need again 16 GB. So what we can do? We can remove 64 GB or we can come to the 16 GB, right? Similarly, we can remove the old hard disk and come to the new hard disk, right? That means what is happening? We just modify the things dynamically as well as in control manner, right?
Yes, sir.
Dynamically, we just remove everything and just dynamically control manner, as well as everything is reverse. Okay. So the reconfigurability can be defined such we say when we are modifying, means we have the capability of modifying dynamically, okay, in a control manner, and that should be in reversible. Okay. When we find such characteristics, then we can say there is some reconfigurability. Now you can just incorporate this capability into the antenna. Then we can define reconfigure antenna is an antenna which is capable of modifying dynamically its frequency, radiation properties in the control and reversible manner, right?
Yes, sir.
So this would be the proper definitions. Okay. No, don't say only just changing from frequency one frequency to another frequency. Okay. Then reversibly we will come the previous frequency. So obviously this is the frequency reconfigurability. Okay.
Yes, sir.
We can alter anything. Radiation properties. So radiation property including beam, okay, pattern, shape, size, everything will come over there, right? You have to control the entire thing, including polarization also.
Yes,
Polarization is a part of. So based on the frequency, pattern, and the polarization, that can be defined as the frequency reconfigurability, polarization reconfigurability, and pattern reconfigurability. Okay, and when we are combining two or more together, it becomes a hybrid reconfigurability, right? These things we can consider. Okay. So basically, so what are the challenges? Means when you are designing, I can say any RF engineers, and you would like, yeah, you guys, your professors ask you to design a reconfigure antenna. So what do you think first? So these are the three questions we have to answer. Okay. Once you are able to answer these three questions, your antenna would be final. Okay. You are able to design any reconfigure antenna. So what are those questions? First, you have to see which reconfigure property needs to be modified. Means what property your professors ask you. Okay. Means what reconfigure property has to be modified. So either frequency, radiation, pattern, or polarization. Okay. If somebody asks polarization reconfigurability, so accordingly you can see polarization. So then you can see once you answer these questions, key polarization reconfigurability, then you can think about that within the structure, whatever radiating element we have, in which radiating, what we can modify that based on that, how we can achieve this property. Okay. So then we are modifying the structure in such a way that to achieve this property, either frequency. So for frequency, we have to increase or decrease the electrical length. Patterns, accordingly, we just modify. Polarization, accordingly, we have to modify. Okay. Once we've got this thing, okay, answer of these questions, elements we are playing this, okay, answer got the reconfigurability properties. Then we have to see how we can just utilize this thing in a techniques, which reconfigure techniques that can minimize the negative effect on the antenna, that means radiation property or impedance characteristics. We have to apply which technique is suitable to achieve the such whatever stated radiation or reconfigure properties. Based on that, we can think about that which reconfigure technique is suitable for our purpose. Okay, that don't affect too much, or we can say don't deteriorate our radiation or impedance characteristics. If you are modifying our structures in such a way that for getting the characteristics, required characteristic polarization, reconfigurability, or pattern is destroyed, they are deteriorated, or shifted, or something else, yeah, your impedance characteristic will deteriorate. So this is not good. It should have minimum effect. Okay. So just choose the technique in such a way that it has some minimum negative effect on its pattern as well as the impedance characteristics. Okay. If your impedance characteristic will change, that means it will affect your bandwidth. This is not desirable. Okay. So yes, I'm skipping this one also. So you guys are knowing very well. I told you about this hybrid reconfigurability, compound reconfigurability. This is a very simple example. So I'm just using this example. Okay. This example. This is very good example. So you can download this from the IEEE transaction also. So the antenna size is very small. Okay, this antenna size is very small, but you can see the frequency range. This is 48 megahertz to 1.5 gigahertz and more. Okay, 1.5 gigahertz and more, 48 megahertz to 1.5 gigahertz and more. The frequency range is used. Okay, so see the step by step evolution. Initially, this is a slot antenna. This is the slot printed antenna in slot antenna. This is the slot, which is responsible for radiation. Okay, the slot antenna. Okay, now this CPW feed is used over here. Now, this particular corner, okay. Initially, this guy got this two frequency about 1.2 gigahertz and 860 megahertz. Okay, 860 megahertz and 1.2 gigahertz. Okay, about this one. Now, this particular corners, you can see in all corners basically connected four more slots. Okay, this is connected. Then for your 860 megahertz frequency come to 460. Okay, is getting. Then again in next example you can see again there are two slots which are connected to this one. In this way, what is happening? The electrical length increases. So your 460 is coming to the 350 meg lower frequency reduces. Okay. Now further reductions means you need basically this guy needs basically 48 megahertz. This for 48 megahertz. What he did? He just connected meander line slot in such a way that to accommodate the entire electrical length which is required for 48 megahertz within the space. Okay, on the both sides, symmetric. The structure is symmetric, so it achieves 48 megahertz. Okay, so obviously they need switching action sometimes because of the control manners. So switching action use the pin diode. They use the pin diodes. So there are pin diode conditions, on and off condition. Based on that, this frequency reconfigurability is achieved. Okay, based on different conditions of pin diode, which pin diode you have to activate. So based on that, suppose this is connected, and obviously we have the bias line is very challenging once. Once you are designing a reconfigurable antenna, the bias lining are very challenging things. So we have to design the bias line very carefully. Okay, means it should be very, very thin. That does not affect basically always bias line is additional structure. So it will affect your radiation performance. So it should be very, very thin, very, very thin. Okay. So that not affect your radiation as well as the impedance characteristics. It should be very, you should be very much careful during this design of this one, right?
Sir, one doubt is there.
Pardon?
Sir, one doubt. Sir,
yeah, please.
Pin diode have inductor and capacitance. In the on state it have
on state and off state. There is on state condition is different, off state condition is different. Yeah.
Sir, so how we can overcome from by this inductor value and capacitor value of the pin diode? Means how we can reduce neglect or neglect the effect of the inductance or the capacitance.
Yeah, exactly. In on state and off state conditions, we have to consider during the design. Okay, when you are considering the design part, so you have to consider that L and C effect.
Yes.
Okay. So it will be a part of your impedance, na? We have to incorporate. You cannot neglect like that. So when you are using the lines, line having the inductance as well as the capacitance, right? Yes. Because of the couplings. So, okay. We have to choose a width of the line in such a way that so that you can nullify. And when you are using the pin diodes, so it's inbuilt defined C and L.
Yes.
Okay. It is fixed. You have to incorporate those C and L during your design part. So it will come. So no need to overcome additionally. No need to work on this additionally. It would be a part of that. So what would be the impedance of basically in the on state and what is the impedance on the off state by considering the pin diode? Okay. So the L and C become the part of impedance.
Yes, sir.
Getting? So you will find according the input impedance at this port accordingly. Once you are getting the input impedance at this port by considering these things, and your characteristic impedance is 50 ohms. Okay.
Yes, sir.
Your ZL would be there. Accordingly, you are getting the bandwidth and reflection losses, right? It will come automatically. No need to work on this one to work on the inductance and capacitance, right?
Means
Are you getting or not?
actually when we are going to connect the pin out, means then it will give the inductive effect. Means it passes the sub-frequency. Means it gives a notch in the S parameters.
Okay, you are getting
Yes.
something else because we never seen. So this is part of design. You're part of design. We should be very much careful during the means you face this problem in the simulation, right?
Yes, sir. Yes, sir.
Okay, I got it. So basically, okay. So before that, I'm talking about something. There is a which software HFSS or something else?
CST software, sir.
CST as well as no problem. Both are same. Only numerical technique is different. Nowadays, there is a hybrid solvers are there. Okay, so you can use any one of them. Okay. So what is happening when you are using the softwares? So there is a numerical error is there. So for defining this LNC, you are using a particular pin diode or you are defining by manually?
Pin diode.
You are inserting particular pin diode over there, right?
Means we have taking as a lumped element. So here we have.
You are using LNC.
Yes, sir.
In terms of line, right?
Yes, sir. Yes, sir.
And you are defining the impedance as a LNC, right?
Yes, sir.
Okay. So one thing is that when you are using this numerical software, so in each and every numerical software, there is a criteria that is called stability criteria. Right? Stability criteria. Do you know about this one? Stability criteria?
No, sir.
You don't know?
No, sir.
Yeah. Okay. So when you are running any simulation software, not talking about CST, HFS or something else, any simulation software based on the numerical technique, okay. So you must check the stability criteria of the software and numerical techniques. Each and every numerical technique having some specific stability criteria. If you read the FEM,
Yes,
it has some FDTD, it has some, okay. And that can be defined with the help of mesh size.
yes, sir.
Okay. Now, in simulation software, how can you check? Basically, theoretically, we are knowing this thing. First, you have to see your solutions is stable or not. Once your solution is not stable, like sometimes you are getting some, whatever you saw right now, you are not getting some notches, some flickering effects you are getting, some spurious effect you are getting from these lines, right?
Yes, sir.
So always this line gives the spurious effect. Okay. So the line width will be very, very careful because if you are putting very thick line, that is harmful. Okay. This line should be very thin because this line characteristics we are defining in terms of LNC. Are you getting?
Yes, sir. Yes.
Yeah. So because you can see the microstrip line, we are defining some width W1. Okay. Having characteristic impedance of 51, right? We are defining such a that. But what is happening in addition to this one, we are getting some spurious radiation. If you plot the electric field, you are getting some spurious radiation. Okay. We can't say the line is perfectly transmitting the signal. In addition to transmitting signal, we are getting some spurious radiation. That spurious radiations affect the pattern of the patches, right? Knowing this one, you can simulate the simple patch antenna using this microstrip line. You can see some spurious radiation over there.
Yes,
that is affected. Okay. So similarly, this spurious radiation you are getting. So just for that purpose, you choose very thin lines. Don't put thick lines. Okay. And thin lines, because in the microstrip case, it is very particular. We have to define for particular impedance. Okay. We are not putting impedance values over there. But for this particular LNC, when you are connecting this one, we are defining what is L and what is C in the case of on state and in the case of off state, right?
Yes, sir.
Individually, we are defining on state, individually defining off state.
Obviously, yes.
So based on that, so then you can avoid. So stability you can check by just making one you're defining is the boundary regions. Okay. So suppose in the boundary region we are getting one results. Okay. Change the boundary. we are getting suppose different results. Okay, that is not acceptable. Whenever you are changing your open region or open boundary, okay, boundary conditions are changing from one boundary to another boundary, your results should remain same. Okay, we can't accept sir 1% change aa gaya ya 0.5% changes hai. But you guys are getting more than 10%. I am saying we can't accept the results of 1% change even. Okay, means whatever simulation results were coming at first instance, in second instance means we are changing the boundary conditions. Okay, it should remain same. ऐसा नहीं होना चाहिए कि one will come, another will come over here. Okay, it is not acceptable. That means your results are not stable. Means when you are moving from one computer to another machine, one machine to another machine, your results are changing even. That is not stable. Are you getting my point now?
Yes, sir. Yes, sir. Yes, sir.
Sometimes you observe this thing when you are moving from one machine to another machine, your simulation results are changes.
Yes, sir.
Yes or no?
No, sir. I have working on other topic.
Pardon?
Some on the other means we can design some design. They maybe have a different result on the when we changing the boundary condition.
No. My question is that did you observe when you are changing from one computer to another computer, your result has been changed or not?
So in my research, I have not seen this changing.
Okay, so sometimes this is one thing because
if we go the other simulation, then means if we
no,
do
I'm not talking about one software to another software. Okay. I'm talking one numerical technique. Suppose CST or SFS, anyone, and you are changing one machine to another machine simply. One laptop to another laptop, yeah, one desktop to one.
I have not checked this.
Yeah, you just check it. Okay, so when you are getting this thing, that is the stability issue. Okay, what is happening? Based on the machine performance, your simulation software optimized and adaptively making the meshes. Okay, based on the RAM and the
yes, sir, yes, sir.
When the software finds the good machines, accordingly just redefining the meshes, adapting process, and mesh size reduces.
Yes, sir.
Okay, so stability depends on the mesh size. Okay, so this stability for fixing, once you are moving from one machine to another machine, result are changes. Yeah, yes, open region, whatever open region you decide, your boundary condition you decide, you change the boundary condition, your results are same without any change, no change in the results. That means you can say your results are very much stable. Okay, but if your results are changing from one position to another positions, yeah, one result to another position, we are getting new result every time for changing the boundary conditions. That means your numerical results are not stable. It has to be fixed, and stability characteristics will be fixed. So that can be fixed by reducing the mesh size. And the condition is that reducing mesh size, you have to do by forcefully. Okay, now you can see, so how can you do this? So now when you are connecting this lumped element LNC, so you can see it is very tiny.
Yes, sir.
Very tiny, almost 0.5 millimeters width, right? Length, 0.5 millimeter length. Okay, so 0.5 millimeter length and width is almost 0.5. Okay, so you can consider 0.5 millimeters. It is very tiny. So once you plot the mesh, you can see, so meshes, we can say the tiny structure is fully covered with the proper dense meshes or not. If it is not properly covered dense meshes, that means the solution is not converged properly at that particular moments. Okay, so you can choose particular components and define the mesh size less than 0.5 millimeters so that proper meshes can be converged over there. Okay.
Okay, sir.
Yeah. So these are the things. Okay.
Okay, sir.
So for the time being, Manoj.
One more question, sir.
Yeah.
I'm concerned. The D1 square, the large square in the center, how is it not coupled RF, regardless of the diodes, to the D2 square? The D2 square seemed to me that if the D1 square is being energized or excited by a 400 or 500 megahertz signal, the D2 squares will be radiatively coupled. I don't understand how the pin diode will stop that.
Could you please repeat the question once again?
Sure. Yeah. The D1 square, I understand it's coupled to the input, to the antenna, okay, and it receives a signal. and you can the antenna resonant frequencies can be adjusted by the diodes. But that is the theory. What I don't understand is that all these pieces of metal surrounding the D1 square, for example, there are 4 D2 squares, they should be coupled, they will couple with the D1 square whether or not the pin diodes are on, it seems to me. Is it because they are touching only in the corners that the coupling is poor? I don't know.
Okay. Okay, I got it. So basically what is happening in this particular structures we are considering, suppose this pin diode. Okay, the pin diode is nothing but simply this is the interconnect between two elements. Okay. This is the interconnect between two elements. This is element number 1 and this element number 2. Okay. Are you getting this thing? This is the interconnect. So in on state means there is a proper connection between one to another. Means current is flowing from one element to element number 2. Okay, it means forward conditions. Forward bias conditions. This is switched on. This means we can say pin diode in on state means switch on. Once is off state, so there is no interconnect. It is free from this one. There is a backup, basically reverse bias state. Okay, in reverse bias state.
I understand that the pin diode can make the DC connection.
Yeah,
but
exactly.
I think that there is so little impact. I would imagine there is so little impact because at radio frequencies, the energy radiates from D1, the D1 square, into each of the D2 squares, whether or not the pin diode is on or off. At 500 megahertz or 600 megahertz, that radiation goes across whether or not the pin diode is on or off.
Oh, we have to think about that. Yeah. We can think about that thing. Okay.
Sir, I think Daniel sir is discussing that if we just don't connect the extra these patches, the D2, D3, D4 with the main patch D1 directly. So if we don't connect it directly, then current flow will not occur. But electric field is affecting those patches, and those patches will act like extra radiating patches. So the effect of disconnecting with the diode will not be that much significant. That's what I think we want to say. But still, by removing or making that pin diode off, we can stop the conduction of current through the extra patch. It will be just electric field which will be affecting that, not the conduction current.
Yeah. Okay.
Yes, sir.
Yeah. Anything else? Manoj?
Yes, sir.
Yeah. So can we stop now?
Yeah. Now it's done, sir.
Yeah, it's done. Because we cannot finish. We need 3-4 hours. Then again, there are a lot of things. So for timing, we can stop. And sometimes students would like to listen. So I am available here. So we can fix in the night also sometimes.
Thank you, sir.
Okay,
Yeah.
so students, if you have any query, please ask. Otherwise, we can conclude the session.
So there are some questions in the chat box. I would like to ask.
You just quickly read the questions.
So there is one question. What is the thumb rule followed to choose the components? Are they fixed? Please throw some light on. Means
what is the thumb rule followed to choose the components? Are they fixed? Please throw some light on it.
I think, sir, Sam was asking about the same antenna we have used.
Yeah. Basically, I told you before. Okay. So basically, that connecting the components is one of the switching techniques. So once initially we got the answers, which reconfigurable property you are looking for. First, we'll just answer this one. Okay.
Yes, sir.
Just wait. Okay. Once we got frequency reconfigurability. Okay. Right now, for present examples, there is a frequency reconfiguration means shifting from one frequency to another. Okay. For that property, so what they observe, the play with the radiating elements. Okay. Frequency, what we need? We need the increase of electrical length. Increase of electrical length, right? Increasing the electrical length with the beta L, playing with the beta L,
Yes, sir.
right? So what is happening? So there are techniques. So with techniques, so switching techniques, we need from one frequency to another frequency. So there is one of the example is pin diode.
Yes, sir.
Pin diode. Okay. Now structure is fixed. Structure is fixed. This is structure is fixed. Okay. This structure is fixed. This structure, you can see this structure fixed. So initially, one frequency getting this one. From this, getting these frequencies. Okay. Now, suppose the guy studied, if we connect 4 more slots by increasing the electrical length, okay, reduces the frequency. This is obvious one or this one. In further, again connected, okay, this will give basically this. Once we change this direction of this slot in this particular direction, instead of that, you can go in different type, your polarization will change. Okay. Nothing will change. Okay, pattern will change. Okay. So initially he's looking for the frequency change. Now, the putting the diode in particular place, so what is needs? Connections. There is a connection between here only. Okay, so we have to connect. The guy has to connect. This is the interconnect. So number of pins, IOs or MEMS switches or variotor diode, it has to select accordingly which direction current would like to flow. Direction of current has to be flow. So you can choose. Okay, anything? It is okay, or you need something else on that one?
Sir, I think it's enough.
Yeah.
Thank you, sir.
Any other question?
There is no question in the chat box. I asked the participants if there is any other question from your side. Anybody?
Sir, one of my question is, what
Yeah.
kind of phasing problem in millimeter wave band
Yeah.
for reconfigurabilities?
What kind of problem facing the millimeter wave?
Yes, sir.
Okay. So in the millimeter wave,
Yes, sir.
basically problems are remain same. Okay.
Okay, sir.
Only
Okay,
in the
sir.
millimeter wave, first we have to choose the materials. Material selection is the first thing. Okay. You cannot select the same material whatever you are setting in the lower frequency.
Okay, sir.
You have to change the material first. Okay.
Yes, sir.
Rest of
Yes,
the
sir.
thing remain same. Okay.
Yes.
Why we are changing the materials?
Because it
Suppose in the lower frequency,
yes,
you guys are working on the RT Duride or FR4 or something else like that.
yes, sir.
Yeah. But
Yes,
the
sir.
higher frequency millimeter range, we cannot use same material. Why? RT Duride, glass epoxy we cannot choose. FR4 you cannot choose. Why?
Because it has a lower
they are
wavelength.
This is too lossy.
yes, sir.
Okay. And if you are choosing lossy material in the millimeter range, our entire signal will go lost. Okay. We lost the entire signals. So we need the low loss materials, very, very low loss materials at the millimeter wave. Okay.
Yes.
First thing is that. And always what kind of elements you are choosing for this reconfigurability? Suppose pin diode you are using. So what pin diode you are considering? Which type pin diode? Suppose we have resistors, we have capacitors, we have inductors as well as pin diode or variotor diode. Which kind of components you are considering?
Chip based.
Chip based, right?
Yes.
So this is called surface mount component.
Yes.
Okay. So when you are connecting this component to the any antenna circuitry, okay, any RF circuitry, you use don't use the solders. So don't use soldering, electric soldering. Okay.
Yes.
Okay.
The surface mounting paste is there. Use that paste and connect the components. Okay. If you use the soldering at any frequency, at the lower frequency, higher frequency, additional losses you are incorporating what there. This is a lossy material.
Okay.
Okay, so you just take care of. So
Okay.
designing when you are designing a millimeter wave, another challenging task would be the biasing circuit. The biasing circuit is always challenging in any frequency, lower or higher or any frequency. Okay, so you should be very, very careful. That does not affect your radiation characteristics, because in the millimeter range, your radiating components are very, very tiny. Okay.
Okay.
And your biasing circuit would be bigger than this one, so that will affect. Okay. So you can design biasing circuit in terms of chip. That would be better. Okay.
Okay. Okay, sir.
So in the millimeter wave, or transmission lines are in terms of chip. We cannot see many components with the naked eye in the millimeter range. We need the microscope so that we can see the line. Okay. And the material, obviously, we cannot use the same materials. Okay. So there is a thin film technology where we can see the semiconductor fabrication technology. Those guys are fabricating the antenna for this reconfigured antennas. Okay. They can do for us. We cannot do by ourselves because we cannot see with the naked eye. That lines we cannot see. In the millimeter range, if we are able to see your line, that means it's not good. You can't say. Okay.
Okay.
So have you seen any microstrip line in the millimeter range? Have you seen? In 100 megahertz range? If you consider the width at 100 megahertz, 100 gigahertz range, the width of the microstrip line 100 gigahertz range, you can choose lossless material, don't worry. So you can see the width of the line. What is the width?
It's very thinner.
Then you will amazing.
Yes.
It is not visible.
Yes, sir.
Okay, so we need sophisticated machines. So it will always printed in terms of chip. Okay, so you can use the same machines for printing the biasing circuitry. Don't use wires also. Sometimes you guys are using the wires for connecting interconnects from here to there as a biasing line, or you're connecting battery. This is not good. That is also affect your pattern. Okay.
Okay.
Yeah. Anything else?
No, thank you, sir.
Sir,
Is there any question for if anyone participant ask question, please ask. Otherwise, we will just conclude the session.
Sir,
Yes, please.
I have one question, very general kind of question.
Yeah.
So this work on this reconfigurable antenna and circuit going, I think, at least last 2 decades, right?
Right.
So what is the current trend on this reconfigurable antenna? What is the future scope of this reconfigurable antenna or circuits?
Yeah, basically in the current trend, satellite communications guys are looking for basically. They need very compact antennas to cover the entire frequency bands. Okay. In the current trends, those guys are looking for the reflector array also to replace the big antennas with the help of reflector array or the wideband. Okay, wideband high antennas. So they are looking for this reconfigurable reflector array. This is the future trend. So satellite communication guys like the ISRO's agency, space agency, they are looking for those antennas. Okay, or not for the small. This small antennas is not good one. So always this is the solution for the complex antenna structures. So reconfigured antenna gives the solution to the complex antenna structures like space agencies.
So I think this topic is still a gray area, right?
Yeah, exactly. So they are looking for, like you can see nowadays basically the space agency, they are looking for antenna on the solar panels because they have solar panel along with the satellites. Okay, so the particular portion is empty, so they are putting the reflector array on the solar panels also. So they don't need additional space for the antenna deployment. Okay, in the same panel they are deploying the antennas on the solar panels, and these are the folded also. And then we are using the active devices for getting the reconfigurability so that they can play with the beam and frequency to cover the entire beam. Okay, so wide bandwidth patterns reconfigurability they can achieve, as well as the polarization also. So sometimes basically they are working on the circular polarization. So sometimes they can switching from LH to RH, left hand circularly polarized to RH circular polarized. They are playing with this one as per their requirements. Yeah. So these are the future trends they are looking for this one. So in antenna there is a lot of viscose always. Okay.
Correct. Even a lot of work on going on this active reconfigurable circuits or filters.
Exactly.
Right?
Exactly. So you guys can think about that.
Yes.
Yeah.
Okay. So with this, I thanks, sir. Thank you very much. It's a wonderful talk. You started with very basics to more a recent trend in planar antennas, or you covered the reconfigurable kind of antennas. It's really wonderful talk.
Defense sector, it is very useful.
Right.
Planar antennas are very useful in defense sector. Whatever antenna I showed you, this is still demanding by our Indian armies.
Right.
Because these antennas are very costly.
Correct, correct, yes.
And they need in the bunch basically. Always the enemy is destroying their antennas. तो रोज गिरते हैं, रोज उनको चढ़ाना होता है.
Yes, yes.
Yeah, this is the demand. Okay.
So I think students got a lot of motivation from your talk. I think they will think of working in the field of this reconfigurable circuits or antenna.
Yeah.
So
Ravi Panwar is there.
Yes,
Ravi Panwar is there. Ravi Panwar is there.
Ravi, just
yeah.
Ravi.
Yeah.
Yes, sir. I am here only. Very good.
Yeah. Hello.
Very good morning, sir.
Dr. Treves,
Morning,
Dr.
good morning,
Treves is there. Dr. Treves, you know Dr. Treves?
Yeah.
He's from IIT Kanpur. He's a Harish sir student.
Yeah. Okay.
Yes.
So he's working on maybe RFID?
Yeah, all are. I mean, he's working, I think, this SIW antennas.
Okay, SIW antennas. Okay, leaky wave antennas.
Yes, and Ravi work mostly on the absorbers.
Absorbers, yeah.
Yes.
Okay, nice meeting you all, guys.
Yeah, so thank you very much, sir. This is a wonderful talk. Thank you very much. It's a very informative and inspiring talk, right? And thank you, this participants, all the participants.
Yes,
and thank you, this student branch. You have, I mean, really organized this event very organized manner or very in well manner, in very short notice, in fact. Okay, so thank you very much and congratulations for another event.
Thank you so much.
Thank you very much.
Thank you, sir, for accepting our invitation to deliver this talk. Thank you very much.
Thank you very much. Bye-bye.
Bye-bye. Thank you, sir.
Thank you, sir.
End the class? Can we end this talk?
Yes, sir. Yes, sir. We can
Thank you
leave
very
it.
much. Thank you very much.
Okay. Thank you.